All right, guys. So thanks for joining in. I'm Costin Lupu. I am a PhD student at University Politehnica of Bucharest, and my research domain is operating systems virtualization. In the recent years, I've been involved in several Zen-related projects. In 2017, for example, I was a member of the team working on the LightVM project, for which you will see some references in the presentation today. Next, for the following 2 years, I was a main contributor for Unikraft, Unikernel, and since January 2020, I've been working on finding a solution for cloning unikernels, which I will present you today. So I'll first start with the motivation for our solution, then we will reveal our objectives, and I'll continue to add a small overview of the related work. And hopefully after that, things will get a bit more interesting and we'll have a look at the numbers. And after that, we'll see how we got those numbers, and we'll end with drawing the conclusions. So I first stumbled upon this problem when I was involved in porting POSIX applications on top of Unikraft. We saw that popular applications were actually depending on fork. For example, Nginx was using fork to create worker processes in order to scale up its HTTP throughput. On the other hand, Redis used fork to create child processes in order to save its in-memory database to persistent storage. Generally speaking, porting POSIX applications on top of a unikernel is pretty straightforward, meaning that you have to come up with the glue code between the application code and the unikernel code. But for fork, that's quite a different story. Especially if we think about the main definition of unikernels being single address space VMs. So where would fork integrate in this picture? Additionally to this generic problem, the mainstream approach for building unikernels is to use static linking, which tends to generate large binaries for applications that have many dependencies. And even if we switch to dynamic linking, as recent research made possible for unikernels, we still won't be able to reuse memory efficiently, such as text, read-only data, or data that is touched very rarely. So in order to have a deeper understanding of how fork could fit in, we have to take a look at the fork semantics as we know them from the POSIX applications. So we know that that fork duplicates the state of a parent process for the child process as well. So each of the processes, parent and child, have an address space. They each have their own demands and life cycles, and this would mean that the state has to be copied for each child, and it cannot be shared among these related processes. And this is, let's say, duplication semantics on a global perspective, but we also have duplication semantics for every component involved in the cloning process. So we just have to think about the file descriptor tables or the signal states, and we also have to support that similarly to adding copy semantics in C++. Moreover, both the parent process and the child process are aware of the duplications, and sometimes there is even a protocol between the parent and the child for using some of the shared resources. Now, having said that, our first objective would be to close the gap towards adding full POSIX compatibility on Unikernels, and this would imply supporting the fork function and everything that fork comes with, such as implicit resource sharing between the parent and the child process, and IPC mechanisms, both being represented by shared memory, regular files, and special files such as pipes and Unix sockets. Of course, we don't want to stick to that, and we want to keep all the fork advantages as we know them and have been reiterated many times in the literature before. Then we want to do the cloning efficiently, meaning that we want to reuse resources as much as possible. And we want to do it fast, meaning that the cloning process itself has to take less time than instantiating the same domain from scratch. Another objective would be to keep transparency, since as you would remember, for forking a process, all you have to do in a POSIX application is to just call the fork function. So we would like to keep the same kind of transparency when cloning unikernels. And the last objective, but not least, we also want to stay true to the unikernel definition, meaning that it has to have a single address space. There was a lot of work, or a lot of related work on this topic, but oftentimes it was suited for specific use cases, and I'm going to present a small overview of those projects that are closely related to my solution. So I'll start with the Snowflock project, which introduced the memory sharing subsystem to Zen hypervisor in 2009. And last year you had a presentation here at the Zen Summit for kernel fuzzing on Zen, presented by Tamas Lengyel from Intel, who added new improvements to the memory sharing subsystem and introduced the new abstraction of VM forking for multiprocess VMs. Memory sharing is a subsystem that we are also using for the unikernel cloning solution. Also related to cloning, but this time to unikernel cloning, we have the Fractal paper, which made the case for application scaling, but scaling is still controlled by the DOM0. And another research project involving unikernel cloning was Skilinks, but which lacked transparency because the parent domain, the child domain, and the toolstack were all involved in collaborating and coordinating the cloning process of the child domain. And this was all done with heavy use of ZenStore communication. And we also have the example of the OSV Unikernel, which fix the problem for some specific use cases by using threads. Now let's have a look at the numbers. So I'll present you today 3 experiments. The first one compares the instantiation times labeled as booting against the cloning times. So for the booting numbers, we measure how long it takes, starting with the instantiation of the XL create command until the VM gets ready. And by ready, I mean the VM can send and receive UDP messages. For the cloning numbers, a single parent is created, and then after it is ready, it will call fork continuously in a loop. And the numbers plotted here represent how long it takes for the fork call. The application is almost identical to the one we used for the Light VM project back in 2017, which is a simple UDP server on top of MiniOS. And we even use the same hardware for this experiment. Now, if you ignore the outliers, you'll notice that the clone numbers are quite okay. The outliers are an effect of the OCaml memory management, because for these experiments we use the OZenStore, the OCaml implementation of the ZenStore daemon. And you will notice in this plot that for the cloning process, the outliers are less frequent and have a lower amplitude, because during the cloning process we have less interaction with the ZenStore daemon, because the operation are batch as much as possible, and the IO negotiation for the front-end drivers is totally skipped. Another observation I have here is related to the first number for booting, the 151 milliseconds. So back in 2017 for Light VM, we achieved 65 milliseconds, and that was for Zen 4.8. These experiments now are run on Zen 4.14. So in the meantime, there is an extra of almost 100 milliseconds addition. And this is actually natural if we think that in time toolstacks tend to add extra functionality with an extra cost that can't be avoided. And this should be another reason for adopting cloning semantics for legacy toolstacks of any kind, actually. We move further to the memory density experiment. We use the same setup here. I forgot to tell you the machine has 16 gigabytes of RAM. So we know that the maximum number of VMs that can be instantiated on a machine is limited by the available memory of that machine. For each VM we used, we configured a total of 4 megabytes, out of which, in case of the clones, roughly half of it was shared among all the clones, and out of the rest, 2 megabytes. 1 megabyte was used for the receiving of the network device. So we started with a 5 to 11 split between DOM0 memory and hypervisor memory. As a side observation, all VMs are allocated from the hypervisor memory. So we would expect to create clones until we'll get an out of memory event for the hypervisor, but as we actually do for the booting numbers. But we had this nasty surprise, and we saw that actually we get an out of memory for the DOM0. So we increased a bit the memory for DOM0 to 8 gigabytes. Basically, we have a 50-50 share, split share here. And our gain got a bit higher to 2.7 as opposite to 1.1 as we had for the first increment, but we still got the out of memory for DOM0. So we got even farther and increased the memory for DOM0. And as you can see in the plot, the DOM0 memory decreases much faster than the hypervisor memory, and it's actually by 1 megabyte per VM. And which you will see that it is exactly the size of the receive ring of the network device. So what actually happens here is that when it is mapping the receive ring, DOM0 gives back 1 megabyte to the hypervisor memory. And there might be a discussion here whether it would make sense to make this behavior configurable and to keep the 1 megabytes to DOM0. Another observation here is that after 2,500 VMs, we managed to save up to 8 gigabytes. And as I said, we share 2 megabytes for all the clones, and that's why the shared numbers are not visible in the plot. Now, as an observation about the memory that is being shared, so memory that doesn't fall under any of the categories on this slide is shared and marked for copy on write. As you saw on the previous slides, an example of memory that is not shared are the I/O rings. And more generally speaking, shared memory won't be shared with the child. In other words, memory that is referenced by the grant table won't be shared. Other types of memory that are particular to the child VM are the special pages of start info, Zenstore, and console, the page table, of course, and the P2M mapping. I have to add to this that the parent domain has to recreate its P2M mapping because it's the most efficient way we can access P2M also in hypervisor. Moving on with the last experiment. In the last experiment, we have the HTTP throughput numbers for an Nginx running on top of Unikraft. We measure this with WRK tool. I need to add here that usually a typical scenario for running Nginx is to create a worker process for each CPU it can use. So we are doing this with worker domains, and each worker domain has an identical network interface with identical MAC and IP addresses. So we need a special kind of virtual switch to be able to handle this and distribute incoming flows fairly. And for this experiment here, we used out-of-box Linux bond configured to hash IP and port values. Now we can see that the throughput for a single worker here is 30 kilo requests per second, and it scales linearly with every worker we add until we reach the limit of the switch, which is in this case 110 kiloseconds requests per second. Now, regarding the cloning process, the cloning process has two phases. The first one is performed by the hypervisor as soon as the clone hypercall gets invoked by the parent domain. The hypervisor will clone the virtual CPU state, will allocate the memory that is particular for the child domain, as we saw in the categories on the previous slide. And it will clone the grant table, the event channels, it will recreate the P2M mapping, and at the end it will clone the page table of the parent. After this, it will notify DOM0 and specifically zenclone daemon by using the notification ring between the hypervisor and the DOM0. Zenclone daemon is the tool that coordinates the second phase, which implies cloning of I/O mostly. So zenclone will next communicate with zenstore and will batch all the operation that will eventually trigger events to all the backends that are registered to the zenstore daemon. And as an example here, the netback driver will get notified, and after it will clone the state of the parent virtual interface, it will trigger a udev notification back to the zenclone daemon. So after all the I/O operations are completed, zenclone daemon will notify back the hypervisor by using the same hypercall but with a different operation, and we'll see more details about the operations on the next slide. I will have to add as a first observation here is that in case that the parent domain uses an 9PFS driver, then zenclone daemon will connect directly, will communicate directly to the QEMU process for notifying the clone creation. And as a second observation, for performance reason, zenclone may cache parent information, which has to be in line with zenstore updates that will be signaled from zenstore daemon to zenclone daemon. Let's have a quick review of the changes. So for the hypervisor interface, a single hypercall was added with three types of operations. The first operation type is enabling cloning globally, and this is performed by the zenclone, is triggered by the zenclone daemon, which also registers the notification ring. Please note that we also have cloning enable operation per domain as a new operation of the domctl hypercall. And this is performed by the XL tool. We'll see soon when. A second operation is the clone operation itself, which can be triggered by either the parent domain or by the toolstack. So similarly to suspend resume, we have to provide the start info frame number. And additionally to classical fork function, we can also create multiple children at once for a single clone invocation. And when the clone operation is called by the toolstack, the parent ID also has to be provided. The third operation of the hypercall is signals the IO completions, and it might have the effect of delaying the first phase of cloning performed by the hypervisor, which can get significantly faster than the second phase. As you already noticed, a new tool was added, the ZenClone daemon, which is in charge with coordinating the second phase of the cloning. I mentioned earlier that Excel enables cloning per domain, and this happens when it sees the max clones parameters in the Excel configuration file, which restricts the numbers of clones that can be created. The Zen control library was also extended with functions wrapping the operations of the hypercall. And regarding the Zen store changes, the C implementation of the Zen store daemon was changed to skip resetting the Zen store page for clones that are introduced, and this behavior was by default for the OCaml implementation. So we got lucky there. As you saw on the HTTP throughput experiment, the worker domains have identical network interfaces with identical MAC and IP addresses. So we would need a special kind of virtual switch to support these types of interfaces. And in the experiment, I used Linux bonds, but the solution also supports obvious groups in case more context is required for the incoming flows. The solution keeps the changes to the backend drivers to a minimum. So as you can see here in these Git statistics, we add only 14 lines of code for the netback driver, and the rest of the changes are for supporting backend drivers in general. In case of the QEMU 9PFS backend, we had to add support for cloning the feed table, similarly to cloning file descriptor table in POSIX. And finally, for the guest changes, we keep the minimalistic approach. Fork is only a wrapper around the cloning operation of the hypercall. And in order to enable inter-domain communication, we can mimic the behavior of IPC mechanisms by using grants for sharing memory and event channels for notifications, only that this time the remote domain ID is specified by a new wildcard value, the DOM ID child, which means that it will be implicitly, the event channel will be implicitly bound between the parent and the child domain by the hypervisor. So we saw that with cloning, we can use the full potential of POSIX applications when running on top of Unikernel. We can reuse resource by reusing functionality as much as possible, and all we have to do is to add small changes to many components. So thanks, and if you have questions, please ask away.
Hello, that was a fascinating presentation. I've got two questions, both relating to graphs you had earlier.
Yeah.
First of all, to do with the XenStore D memory overhead, specifically the OCaml variant. You had a spike every few domains. What exactly was that? Because one thing we have discovered recently and deleted in OXenStore D was a second garbage collector written in OCaml in OCaml.
Makes sense.
Which version of Zen did you check that against? Zen 4.15 should have one garbage collector deleted from.
Perfect. So these numbers are for 4.14.
Okay. I would be very interested to see a graph of that with Zen 4.15 instead. If there are any other problems, I can put you in contact with Edwin, who is also doing a number of improvements in this area. He would be very interested to see if we have further issues like this to be working on. The other question was about the RX ring sharing. So if you go forward a couple of slides, you had the DOM0 memory changing. I didn't quite follow the reason behind that.
So let's say when the netback driver maps the RX ring, it will give back by memory ballooning the 1 megabytes to hypervisor memory.
That's bizarre. Shouldn't be doing that. Are you using PV or PVH DOM0? PVH DOM0 has a known bug in this area that no one has got around to fixing, but PV DOM0 shouldn't be doing that.
All right, I have a look at that. But
there's a general issue with Linux in that there's a confusion between the memory hot plug interface and ballooning, because ballooning's really giving memory back to the hypervisor, and memory hot plug. What you need is to be able to make some struct pages appear for memory that you have either mapped or not. There have definitely been bugs in the past where that has got confused. So it's possible that a newer DOM0 kernel will behave differently. If you still see that problem reoccurring, we would like to find it and fix it, because that is not behavior that we want or expect to be occurring.
And this was added, I guess, a couple of years ago, because in 2017 it didn't happen for the light beam.
To be honest, there's quite a lot of churn in Linux. But yes, this sounds like a bug that we ought to fix.
All right.
Other than that, very, very, very interesting.
Thanks. So we have time for one more question. Yeah, so someone asked in the public chat, one way to reduce memory consumption would be to let the parent and child optionally share a RX ring and backend device. So yeah, there is a reason why the RX string is not shared among the parent and the child. So technically, the child can still if we apply copy on write for the shared ring, the child, one of the domain actually can steal the RX ring and owns it by itself. If we share the Eric's ring without copy on write between the parent and the child domain, then we'll need some kind of protocol of arbitration between the two entities. So this is possible, but as a specific, as a particular behavior. So I'm not sure if this answered your question.
I think another point towards this is that as soon as you're starting to talk about three DOM IDs, you've got the back end in DOM 0 and a front end in the parent and a front end in the child. The Zen model doesn't have a concept of three-way communication like that.
Yeah.
All grants and all events are strictly bidirectional.
Yeah, maybe
until you get to transitive grants, but no one uses transitive grants.
All right, didn't know about that. Is it supported in the upstream code?
It's there. How well it works is problematic. Basically, transitive grants were there to try and let you chain front end to back end. So you could go front end to back end to front end to back end.
All right.
But suffice it to say, it is a fertile source of issues.
All right.
If you have just a moment more, Edvin's actually joined us again. So if you mind discussing the XenStore things again, that would be very helpful.
All right. Yeah, I'll have to rerun the experiment.
So can you go back to the earlier slide?
Yeah. So what you're saying makes perfect sense because this was triggered by something in OCaml library, let's say, OCaml application, not by the interpreter. So it makes sense that it might come from a garbage collector running on OCaml level.
Are those latencies that keep increasing with the number of instances?
These are spikes.
Mm-hmm. So in the current version of XenStore, so besides the OCaml garbage collector, there is also a second garbage collector that collects strings, which I sent a patch to remove. And that one has run periodically. So even if you had no activity, it was running periodically, and it's O of n. So the more domains you have, the more time it spends.
So I committed the patch to remove that garbage collector in Zen 4.15. These results in the graph are from Zen 4.14, so didn't have your fix in.
Okay, so it could be that. It might be worth rerunning with 4.15 when you get a chance to see if it has...
makes perfect sense, right?
Are they about 30 seconds apart, these spikes?
Well, this is not, it might be depending on the time, but my observation was that it was depending on the amount of on the size of the in-memory database of the in-memory value store.
Yes, of course, you got, even after my patch, you still got the OCaml garbage collector, so that would still have an overhead if you got a very large tree. It needs to walk it every time it tries to freeze something.
So, as I understood it, the patches are on their way to be upstream, right? It's not upstream yet.
4.15 has those patches committed, as Andy said. So if you try 4.15, you should be fine.
All right.
So you should see an improvement. It's not going to make the problem go away completely, but you might see an improvement. And if not, then let us know. And there's probably something more to investigate here.
Yeah.
So if I want to reproduce this, what do I need? Do I just need to run lots of domains and have basically the default tree that comes with those domains?
You can even write many entries in the XenStore. Just write a huge arrays of strings.
Mm-hmm.
We have plenty of code doing that right about now.
Yeah.
As presumably everyone saw, there were a very large number of XenStore security issues a while ago, which had been worked on for a long time. But yes, we would certainly like to understand this and try and improve it if possible.
Another thing that might cause you issues is if you got lots of domains. Basically, XenStore walks all the domains whenever it got an event on any of them. So it's not really, so it's got a select, but that's only used for unique sockets. For memory mapped rings shared with guests, if it receives an event FD, it looks at everyone, not just the guest that sent it. So again, that's some potential OFN activity when you did an OFN one of activity in the guest, right? So that, but that slows down with the number of instances, not with the number of entries.